In today's video, I want to talk about the small cardinals, that is the finite and countable cardinals. We've set up in the previous videos that every set has a cardinality, and we know how to check if sets are larger than each other. We can do this using injective or surjective functions. Uh, Many of the sets we care about in mathematics are actually quite small. They are what we call finite, and so we want to get a handle on the smallest of the cardinals. Before that, I want to talk about the smaller infinite cardinals. In particular, I want to talk about Aleph naught. So, and this is where we'll get our numbers from. So, let's see. So, definition. So, remember from the axiom of infinity, there is a set which has the empty set in it, and it has the successor of all its elements in it. So, we define, let uh, X be a set with the empty set in X and such that for all x in X, the successor of X, which remember is just X union the set containing X, is an element of larger X. So it's closed under going to the next one. We think of these as numbers. The empty set will be 0, and the successor of 0 will be 1, and so on. So this will give us essentially an infinite set. And I wanted to define the natural numbers like this. So the natural numbers are the smallest set with this property. We define Aleph naught, or equivalently the natural numbers, to be the set of X in X such that X is in Y for all Y with the properties given above, with empty set in Y and Y plus in Y for all Y in Y. So you can think of this as the intersection of all our sets which contain the empty set and are closed under successor. So this is the smallest set that exists, which contains the empty set and is closed under successor. And because it's the smallest set like this, you can see that it doesn't depend on the choice of x. So this is actually a well-defined set. So basically, you can say this is the set of things which is the smallest set which contains the empty set and is closed under successor. And such a set exists by the axiom of infinity. Okay, so there's a few things we want to know about this. First, we want to know that essentially the structure of it. So it contains the empty set and all the successors of those things. I want to show that every element of the set is the successor of one of the elements except the empty set. And I want to show that this is in fact a cardinal. So this will be the smallest infinite cardinal, which we'll get onto when you find what infinite means. So um, here's a theorem about this set. Before that, we need to find it's an ordinal. But so the set Aleph naught is a cardinal. So it's an ordinal, which is not in bijective correspondence with any smaller ordinal. And for all, let's call it n in Aleph naught, either n is the empty set or n is equal to the successor of something m for some m in Aleph naught. So the former condition will give us that as a cardinal. The second condition will essentially give us the foundation for using induction, which is a powerful proof technique we'll use later. Okay, so proof. So why is this true? Well, first I need to show it's a cardinal. So to show it's a cardinal, I first need to show it's an ordinal. And my standard technique for showing things are ordinals is to show that all their elements are ordinals, and to show that it is a transitive set. Okay. So uh, so first I'll show that all the elements of Aleph naught are ordinals. So let's say n be the set of things x in Aleph naught such that x is an ordinal. I want to show that n is in fact all of Aleph naught, because I want to show that all the elements of Aleph naught are ordinals. Okay, well, we have n is a subset of Aleph naught by assumption. I will show that Aleph naught is a subset of n. Aleph naught is a subset of n. This will show that every element of Aleph naught is an ordinal. Well, first, what is the definition of Aleph naught? Well, it's the smallest set which contains the empty set and is closed under the successor operator. So I just need to show that the empty set is an n and n is closed under the successor operator, and I will have done that. So we show the empty set is an n, and for all, let's say, alpha in n, alpha plus is in n. Well, the empty set is an n because by definition, the empty set is an Aleph naught. So, and uh, so the empty set is an n because the empty set is an ordinal. Okay, so what I do is it closed under the successor thing. So if alpha is an n, then alpha is an Aleph naught because n is a subset of Aleph naught. And so alpha plus is an Aleph naught because Aleph naught is closed under taking successors. Uh, as Aleph, so as alpha plus is an ordinal. Remember, the successor of any ordinal is an ordinal. It follows that alpha plus is an n because it's an Aleph naught and it's an ordinal. And that's the definition of n. So we know that n is in fact equal to Aleph naught. So Aleph naught consists entirely of ordinals. Thus, every element of Aleph naught is an ordinal. Okay, so to conclude that it is in fact an ordinal itself, I only need to show now that it is transitive. Okay, and I'll do this in a similar way. So we next show that every element of Aleph naught is transitive. Oh, sorry, the yeah, every element of Aleph naught is contained in Aleph naught. So every element of Aleph naught is a subset of Aleph naught, I should say. Is a subset of Aleph naught. And we can do this using a similar idea. Okay, so again, I'm going to have a new set. I'll call it n prime this time. Let n prime be defined to be equal to, say, alpha in Aleph naught, such that alpha is a subset of Aleph naught. Same idea as before, n prime is a subset of Aleph naught. To show that Aleph naught is a subset of n prime, I just need to show that n prime contains the empty set and is closed under successor. So note, again, the empty set is in n prime because it's in Aleph naught, and the empty set is a subset of Aleph naught. Also, if, say, beta is an n prime, I just need to show that beta plus is an n prime. Then beta plus, this is equal to beta union the set containing beta. So this is in Aleph naught by definition of Aleph naught. And is it a subset of Aleph naught? Well, beta is a subset of Aleph naught. Beta is a subset of Aleph naught. And beta is an element of Aleph naught because beta is in n prime. This gives me that all the elements of beta plus are in Aleph naught because the elements of beta are, and beta is itself. So beta plus is a subset of Aleph naught. So thus, n prime is equal to Aleph naught. So Aleph naught consists entirely of elements which are subsets of Aleph naught, and they are ordinals. It follows that Aleph naught is transitive, so Aleph naught is an ordinal. Okay, so now I have an ordinal. I'm getting close. I next need to show that I have a cardinal, and I want to do uh, basically a similar idea to before, but I will first prove the related point in the theorem. So my theorem is had another thing, which is a tool for letting me use induction, and I essentially want to use induction for the latter part of this, showing that it's a cardinal. So I will now show that everything is either the empty set or the successor or something in, and I can do this uh, using the same idea one more time. So let n prime prime be the set of things in Aleph naught, such that alpha is the empty set, or there exists uh, beta in Aleph naught, such that alpha equals beta plus. And I will show that this is everything using the same idea. Well, it contains the empty set. So note the empty set is in n prime prime because it's the empty set, and that's one of the conditions. And if uh, alpha is in n prime prime, then alpha plus is in n prime prime because alpha is in Aleph naught, and alpha plus is the successor of a thing in Aleph naught. So it's a thing in Aleph naught which is equal to the successor of a thing in Aleph naught. So again, n prime prime equals Aleph naught. So I know that Aleph naught is an ordinal, and every element of Aleph naught is either the empty set or the successor of something in Aleph naught. And we can use this to show that it is in fact a cardinal. Okay. And this is essentially the basis for induction. We know that if we can prove something about the empty set, and we can prove something about the successor of anything we've already proved something about, then we know that uh, it follows for everything in else not. This is essentially how induction works. Okay, so it remains to check that Aleph naught is a cardinal. Okay, so if it's not a cardinal, that means it's in bijective correspondence with a smaller ordinal. Okay, so if Aleph naught is not a cardinal, then the cardinality of Aleph naught, which is defined by the previous video, this is smaller than Aleph naught. So it's an element of Aleph naught, because that's what it means to be smaller than an ordinal. It means to be an element of. Okay, so in this case, we're going to have some sort of nonsense, and our contradiction will lie into our previous assumption. So this means that the cardinality of Aleph naught is either the empty set, or it is the successor of a thing in Aleph naught. Okay. Okay, there are two cases. To consider. One, if the cardinality of Aleph naught is the empty set, then there is a bijection from the empty set to Aleph naught. There is a bijection, let's say psi from the empty set to, sorry, my pen is breaking. The empty set to Aleph naught, but this is impossible because the empty set is an element of Aleph naught, which means this function cannot be surjective. But phi is in Aleph naught, and phi is not in the image of psi. The image of psi is the set of things which are mapped to by psi. The empty set is not mapped to by psi because nothing is mapped to by psi because its domain is the empty set. Okay, and this is a contradiction. So uh, psi is not surjective. This is a contradiction. This X with dots around it is the contradiction symbol. Okay, so 2. If Aleph naught cardinality is equal to n plus for some n in Aleph naught, then I'm going to reach another contradiction. Yeah, essentially I'm going to you know, use the idea that n plus is a finite set to get a contradiction. We'll talk about finite sets in a minute, and this idea will come up again. But let's basically do the thing. Then there is a bijection psi from Aleph naught to n plus, and I can modify this bijection a little bit to make sure I have a little bit of an idea of what's going on. So we're going to define a new function, which is I'm going to use the modify psi. So yeah, the empty set is an element of Aleph naught, so I can map it using psi. So note that note the empty set apply psi is an element of n plus. I want this element to be n. It might not be n, but I can fiddle with it so that it is. Okay, so we define a bijection. Let's call it g from n plus to n plus by g of, let's say, a is equal to, and there's two cases, I'll map it to just a if a is not equal to n and a is not equal to the empty set psi. So I want the empty set to go to n, so I'm basically just going to compute the thing so that it does. I'm going to map it to n if a is equal to the empty set psi. I'm going to map it to the empty set psi if a equals n. Note this is a bijection. It's onto. It maps to everything that's not n or psi by just itself, and it maps to n by empty set psi, and it maps to empty set psi by n. It's also injective. It doesn't send two things to the same thing. It sent two things to the same thing. This would be, it can't happen in the first case. It could only happen in the other cases, and it does not. If it's sent, the only thing it sends to n is the empty set psi, and the only thing it sends to empty set psi is n. It might be the case that empty set psi equals n, but in this case, with the two cases, it just collapsed into one case. So this is a bijection. Okay. So note that the psi composed with g is a bijection because it's the composite of two bijections from Aleph naught to n plus. And now this bijection has the property that it maps the empty set to n. And the empty set psi composed g is equal to n. So I can just assume that my bijection maps the empty set to n. Okay. And so let's say psi prime denote this new thing. Psi composed g for brevity. And no, psi prime maps the empty set to n. Okay. So where am I going with this? Well, the idea is I'm going to essentially modify my bijection again so that it only maps every natural number to like n, or the things less than n. And this will be a contradiction because I'll have like a smaller cardinal. Okay. So now I'm going to define a new thing. So let's say f from Aleph naught to Aleph naught be defined by f of alpha equals alpha plus. This is well defined because every successor of a thing in Aleph naught is an Aleph naught by construction. And in fact, this is an injective function because it maps uh, it doesn't map any two things to the same thing. If alpha and beta are different, then alpha f and beta f are different because the largest element of alpha f is alpha, and the largest element of beta f is beta. And note that f is a function from Aleph naught to Aleph naught. And in fact, it doesn't map anything to the empty set. This notation means you take the set of things which are not equal to the empty set. So it's the set of things in the left set which are not in the right set. It is a bijection. It's injective for the reason I said before, and it's onto this set because by definition of Aleph naught, every element of Aleph naught, that's not the definition, but by the property I proved a second ago, every element of Aleph naught is the successor of another element of Aleph naught except for the empty set. Okay, so F composed with psi prime is injective. And I know the image of this thing is precisely n. And the image of f composed psi prime is equal to n because the only thing missing from the image of psi prime is the thing which is missing from the image of f. You apply psi prime to it. The only thing missing from the image of f is the empty set, and psi prime maps the empty set to n. So now this thing is just n plus, without n, in other words, n. Okay, so now the point is I now have a bijection from the Aleph naught to n. Okay, so there exists a bijection from Aleph naught to n, which is a contradiction because n is smaller than n plus. Is a contradiction as n is an ordinal and it's strictly less than n plus, which is the cardinality of Aleph naught. I've mapped Aleph naught bijectively to a thing which is to a smaller ordinal than its cardinality, and the cardinality of Aleph naught is the smallest such ordinal. So this is a contradiction. Okay, so we can now conclude that Aleph naught is a cardinal because it's not in bijection with any of its elements, which is good. Aleph naught is called countable infinity, and this is the set of natural numbers. So notes. So, Aleph naught. This is referred to as countable infinity. That's the name of this size of thing, countable infinity. And is also referred to as, also called n. This is the set of natural numbers, or omega. We think of it, you use this n symbol for natural numbers, and we think of these as numbers. We use the omega symbol, and we're thinking of it as an ordinal. And we use Aleph naught, and we're thinking of it as a cardinal, which is why I used Aleph naught in the previous theorem, because I was proving it was a cardinal. Okay, so now I have this notion of countable infinity. I want to talk about the smaller things. These smaller things are finite things. I want to talk about what it means to be finite. Before that, I need some notes about injections and surjections, which will come up in the definition of finite. At least injections will, the way I'm defining it, there will be equivalent definitions. So first, side notes about injective and surjective functions. Okay. We can talk about being injective and surjective more sort of algebraically in terms of one-sided inverses, and this will be a useful notion. So, definition. So if f from x to y is a function, and g from y to x is a function, then we say one of the followings. G is a right inverse for f if f composed with g is equal to the identity function on x. So here we take the function which maps every element of x to itself. So this g undoes x, f on the right. And you can guess the other ones. G is a left inverse for f if g composed with f is equal to the identity function on y. And so we just say g is an inverse if it does both, or perhaps a two-sided inverse if we want to clarify things. And inverse for f if g is both a left and right inverse for f. Okay, and these notions correspond to our previously established notions of being injective, surjective, and bijective. And I will, of course, prove this. So theorem. If f from x to y is a function, then one f has a right inverse. So here, sorry, it's a technical thing, where x has to be non-empty for this to be true, with x not equal to the empty set. Then f has a right inverse if and only if f is injective. 2, f has a left inverse if and only if, wait, I double f, this is shorthand for if and only if and only if f is surjective. 3, f has an inverse if and only if f is bijective. These things will come up in the notion of finite in a minute. Okay, so proof. There's 3 things to prove. So 1, if f has a right inverse, it has to be injective and vice versa. So if f has a right inverse, and a not equal to b are in x, then let's call it right inverse g. Then a f is not equal to bf. This is what I want to show, as if af equals bf, then afg equals bfg, and afg is equal to a because fg is the identity, and bfg is equal to b, which is the identity, and this is a contradiction. Okay, so it follows here that if it has a right inverse, then it's injective. Okay, so if f is injective, then I can just define a right inverse for f. And here is where I have to use the fact that the domain of f is non-empty. Then we define g a right inverse as follows. So first, fix an element of x because it's non-empty. So fix x in x, then g of a is equal to the thing which f maps to a if it exists. So b if f of b equals a, and this b is unique if it exists because f is injective, and just map it to x otherwise. And in this case, it's pretty easy to see that g is a right inverse for f. Okay, 2. I need to show that being surjective is equivalent to having a left inverse. So if f has a left inverse, g, and I have something y and y, the codomain of f, I need to show that it's the image of something. Then y is equal to y gf, because gf is the identity, and in particular it's equal to yg, apply f, so y is in the image of f. So f is surjective. If f is surjective, I need to show it has a left inverse. F, here I'm going to use the axiom of choice. If f is surjective, then uh, let C be a choice function. You might notice this is quite similar to the arguments in the previous video. A choice function for the power set of x without the empty set. So I can take any non-empty subset of x and choose a thing, and define g from y to x by g of y is equal to, you take y pre-image under f, which is you defined in the previous video, and then you just take the choice function applied to that. And this is a left inverse for f. Okay, so that's that. And then bijective. So if f is bijective, here's an important note. Not only does it have a two-sided inverse, but if I have any left or right inverse for f, they will in fact be a two-sided inverse. So I guess I can add to this theorem. Uh, in this case, all one-sided inverses are two-sided. This may be a useful thing to keep in mind. Okay, if f is bijective, then it has a left and right inverse, and it has a left inverse G and a right inverse, let's call it GL, and a right inverse GR. I'm going to show that GL equals GR. This will conclude that they are both two-sided inverses. So GL, this is equal to, here I'm doing some algebra, and this is equal to GL composed with FGR, because FGR is the identity, and by associativity of composition, this is equal to GL composed, GL F composed with GR, which is equal to GR. So GL equals GR is a two-sided inverse for F. And this works for any choice of GL and GR as required. Inverse for F. And then the converse, if it has a two-sided inverse, it's bijective. Well, it has to be both injective and surjective by the previous 2 points. So converse follows from 1 and 2. Okay, so I now have a way of describing injective, surjective, and bijective using inverses. So why did I do this? Well, I mean, it's useful throughout all of math, basically, but it'll be useful in a second when I talk about being finite. Okay, so I'm finally ready to start talking about things being finite. So, definition. So what does it mean for a set to be finite? We say that a set X is finite if there is no injective function f from x to x, which is not surjective. So every injective function from x into itself is a bijection. I can't, move the points in x around in such a way that I now have more points left over. That's what it means to be finite. And there are many equivalent ways of viewing being finite, which is essentially the reason I was talking about the injective and surjective thing before. So, um, the empty set is finite, for example. All the injectives are just the empty function. But more importantly, there's a finite essentially notion of size. So we can talk about it in terms of cardinals, and that's the way I want to say we can talk about it now. So there's a theorem which gives you the equivalent ways of viewing being finite. So the following are equivalent for a set X are equivalent for a set X. And first I should point out if being infinite is just being not finite. And we say X is infinite if it is not finite. So the following are equivalent. 1, X is finite. So it's finite. 2, uh, there is no surjection from X to X, which is not an injection, so it's like the other way around. There is no surjective function f from X to X, which is not injective. And 3, this is the one about size. The cardinality of X is small enough. And small enough means smaller than aleph naught. So the cardinality of X is less than aleph naught. So I can think of being finite as just being, the cardinality of X is like a natural number. Remember, aleph naught is the set of natural numbers. And being less than aleph naught means you're an element of aleph naught. Okay, so these equivalent things are useful because we can think of it in terms of either injection and surjectives, as we were doing with cardinals before, or we can think of it in terms of just being a natural number in size. Okay, so proof. Well, 1 and 2 being equivalent essentially follows from our previous shenanigans. So I will show that 1 and 2 are equivalent, and then I'll show that 1 is equivalent to 3. So we first show 1 implies 2, and 2 implies 1. So for 1 implies 2, if it's finite, that means every injection from X to itself is a surjection. So if I have a surjection, I need to show that it's an injection. So uh, so if so here's 1 implies 2. So if f from X to X is surjective, I need to show it's injective. Then this means f has, because it's surjective, it has a left inverse. And here I can assume the sets are not empty because these are clearly equivalent for being an empty set. These are all just true because there's only one function from the empty set to itself. So then if it's surjective, it has a left inverse. There is a left inverse G for f by the previous theorem. And here G has a right inverse because f is a right inverse for G. As f is a right inverse for G, we know that G is in fact injective because it has a right inverse. G is injective. Okay, so now I have an injective function from uh, from X to X, and I know that it inverts F. And in fact, here, because it's injective and X is finite, that means G is also surjective. And so G is surjective. Because G is surjective and injective, it's bijective. and that means that F is a two-sided inverse for G. And that means, of course, that it is injective and surjective is bijective. So F is also bijective by the previous comments, bijective, which is what we wanted to show. So I know that if it's finite, then every surjection is in fact an injection. In fact, it's a bijection. Okay, and similarly, 2 implies 1, it's like exactly the same. If F from X to X is injective, it has a right inverse. There is a right inverse G from X to X, which is surjective. So G is bijective because every surjection is an injection by the assumption of 2. So G is bijective. And then the same idea as before, F is a one-sided inverse for it, so F is also bijective. So F is also bijective. Okay, so 1 and 2 are equivalent. I now only need to show that 1 and 3 are equivalent. And we've essentially done the work for that earlier on in the video when we were establishing that Aleph naught was a cardinal. So we now show 1 is equivalent to 3. So I just need to show that if I think it's finite, then its cardinality is strictly less than Aleph naught. And I need to show that if its cardinality is strictly less than Aleph naught, then it is finite. Okay, so so for 1 implies 3. If the cardinality is greater than Aleph naught, if cardinality of X is greater than or equal to Aleph naught, then we can assume without loss of generality that X is an ordinal greater than Aleph naught because we can replace it with its cardinality. And assume, using the same ideas from the previous videos, X is in fact equal to the cardinality of X. Then from the idea before, Aleph naught is a subset of X. So Aleph naught is a subset of X, and I can define an injection which is not a surjection, the same way I did before. We define F from Aleph naught, so sorry, from X to X by F of alpha equals alpha plus if alpha is in Aleph naught, and alpha if alpha is not in Aleph naught. Okay, this is well defined because every element of Aleph naught has a successor in Aleph naught, which is thus an X, and the other things are an X by assumption. So this is not surjective by the same as before. It does not have the empty set in its image. So empty set is not in image F. So F is not surjective. And I know that it is injective because the same idea as before, it's injective on Aleph naught and it fixes everything else. F is injective, which is a contradiction because we assumed that X was finite. A contradiction. Okay, so almost done. We just have to show that 3 implies 1 now. So finally, 3 implies 1. I need to show that if the cardinality is less than Aleph naught, then it is finite. And we basically did this before. We did this by taking a function and modifying it by swapping 2 elements. So suppose the cardinality of X is less than Aleph naught, and they will show that it is finite. So we did the empty case already, so we can assume X is not empty. And we know that every element of Aleph naught is either 0, the empty set, is equal to the empty set, or is the successor of an element of Aleph naught. So we can assume, without loss of generality, that X is equal to n plus for some n in Aleph naught. And I will essentially use the principle of induction here. I can assume this n is the smallest counterexample because aleph naught is an ordinal, it's well ordered. So if there is a counterexample, I can choose the smallest one. So let n and aleph naught be the smallest element of aleph naught such that n plus uh, is not finite. So I'm starting with something which is has say x is my finite set, which has cardinality in aleph naught. So I'm now just assuming that I have the smallest one. If there's any one, there is a smallest one, and I will get some contradiction. Okay. So how do I do this? Well, I'm going to take some injection from uh, n plus to n plus and show that it's actually a surjection. So I'll contradict this by showing that it actually is finite. So let f from n plus to n plus be an injective function. Okay, we show that it is surjective. So I want to fiddle with this a little bit. So I want to send n to n. F might not send n to n, but I can just fiddle with it so it does. So let g from n plus to n plus be defined by g of a is equal to, same idea as before, a if a is not equal to n and a is not equal to n f, and if it's either of those, I send it to the other one. So n if a equals n f, n f if a equals n, and this is a bijection. And note g from n plus to n plus is a bijection. So f compose g is injective. It's a composition of two injective functions, and is surjective if and only if f is surjective. It is surjective if and only if f is surjective. Okay, so I just need to show that this is surjective. So let f prime be defined to be this thing. I'll show that this is surjective, and that will be done because then we'll conclude from this that f was surjective, and thus n plus was finite, which is a contradiction because I assumed it was the smallest counterexample being finite. Okay, so we need to show that this is surjective, and note that f prime maps n to n, and note f prime of n equals n, which means f prime defines a function from n to n. So for all, let's say, a and n, we have a f is not equal to n because it maps n to n, and a is not equal to n. So f prime. So f prime defines an injection from n to n. Now, n is either the empty set or it's the successor of a smaller cardinal. So, this is essentially by induction. So, by the choice of n plus, the smallest counterexample, it follows that for all a and let's say so for all b and n, there is a and n with a f prime equals b. Okay, because I have a function from n to n, which is injective. If n is the empty set, then this is clearly true. If it's not the empty set, it's the successor of something, and it's the successor of something smaller than n. So every injection from this thing to this thing is a surjection by assumption, because n plus was the smallest one, which doesn't do that. So f prime contains every element of n in its image, and it also contains n in its image because we just said it did it maps n to n. So for all a in n, union n, there is b in n union n. This is the definition of n plus with f of a equals b. It's the b from before. It's the a from before. If a is an element of so it's for all b and thing there is an a. So if b was in n is the same a from before, and if it's equal to n, then we just choose a equals b, a equals n, and because f prime maps n to n, that's good enough. Okay, so I've concluded that f prime is a surjection, which means f is a surjection, which means n plus is finite, which is a contradiction because that was the smallest finite thing. So we have now concluded the proof that these definitions of finite are equivalent. QED. Okay, so we have now set up the finite, uh, ordinals, and the smallest infinite ordinal, the countably infinite ordinal, countably infinite cardinal aleph naught. And there's an immediate corollary of this, which is sort of unsurprising, but I haven't actually stated it yet. So every finite ordinal is a cardinal. So in fact, the all of the ordinals which are small enough are cardinals. So useful observation. Every finite ordinal, remember from the previous thing, this just is equivalent to saying every ordinal less than aleph naught, ordinal is a cardinal. Now, why is this? I guess I can prove this. So I just need to take a finite ordinal and show it's a cardinal. So let alpha be a finite ordinal. Well, if it's not a cardinal, then there's a bijection from alpha to the cardinality of alpha. I guess I don't need to do this with contradiction. So let psi from alpha to cardinality of alpha be a bijection. Well, the cardinality of alpha is a subset of alpha because it's an ordinal which is less than alpha. And because alpha, so this is like an injective function from alpha to alpha. So psi from alpha to alpha is injective, which means it's surjective because alpha is finite. So image psi equals alpha equals the cardinality of alpha. Let's write like this. The image psi is equal to the cardinality of alpha by assumption, and it's equal to alpha because alpha is finite. Okay, and alpha is equal to its own cardinality, so it's a cardinal. Okay, so we now have our hierarchy. All the finite things, all the finite ordinals are cardinals. The first infinite ordinal is also a cardinal, aleph naught. It turns out the one after that is not a cardinal. It's not too hard to prove that. But yeah, let's just leave that as this for now. Thank you.